Good afternoon, everybody. In the last class, we have seen introduction to primary and secondary batteries. So today we will see secondary batteries, in that lithium-ion batteries and lead-acid batteries. So I am Dr. R. Srinivasan, working as Associate Professor in the Department of Chemistry, Freshman Engineering, Institute of Aeronautical Engineering. Okay. So in the last session, we have seen what are primary batteries, what are secondary batteries, what is the difference between primary and secondary batteries, all those things. So we are going to see more detail about the secondary batteries with respect to lead acid and lithium ion batteries. Okay, lead acid batteries. This is very commonly we are seen in many places. Lead acid batteries, your car batteries and inverter batteries, UPS batteries. Many of these things we have seen it in our day-to-day things, which we use are lead acid batteries. So it's the most common large capacity rechargeable batteries, without doubt. Lead acid batteries are most common large capacity rechargeable batteries. They are very popular because they are dependable and also less expensive. Okay, on a cost per watt basis, that is output energy basis. Okay, so they are very popular because of less expensive and cost per watt effectiveness. Okay, now, this makes the battery cost effective for automobiles, electrical vehicles, and also, as I said, inverter batteries, UPS batteries. So this is something people can afford to easily, and also performance wise it's better. Okay, so this is the just representation of lead acid battery. We have lead as a negative electrode, and the positive electrode is lead dioxide, PbO2. There will be a separator between these two, cell divider, okay, between the cells. This is negative terminal, this is positive terminal, this is a protective casting. So this is just a rough picture of how a lead acid battery, car battery or inverter battery looks like. Okay. It's just an example. It may have different different output based on the output and the number of cells. The dimension will vary, but this is just one of the examples. Okay, so in lead acid batteries, PbO2, lead dioxide, is a positive electrode. Lead is a negative electrode. Dilute sulfuric acid, 40% concentration, acts as an electrolyte. And when the battery discharges, the positive and negative electrode turns into same lead sulfate. Okay, and the sulfuric acid electrolyte turns into water. Okay, so there are two different types of lead acid battery. One is vented type. Another one is VRLA, valve regulated lead acid type. So basically, vented type is also called liquid or flooded battery. Valve regulated, it's a type of battery, is also called sealed battery. It is often used in uninterruptible UPS, uninterruptible power supplies, UPS. This sealed battery or VRLA, valve regulated lead acid batteries are used. Okay, so as I told already, so we have seen here lead dioxide positive electrode, lead negative electrode. So again, if you see anode, sponge metallic lead, cathode, lead dioxide. We can also say it's a peroxide, it's a form of peroxide, lead peroxide. Okay. Electrolyte is aqueous H2SO4. The EMF produced by this cell is 2 volts. Okay. So what is the cell reactions? At anode, oxidation, cathode reduction. So at anode, lead gives at anode lead 2 plus 2 electron. So remember this sulfate, basically it combines with sulfate to form lead sulfate. Okay, so this is the holes because of this anode. Cathode we have lead dioxide. Actually, lead, we call it spongy metallic lead because it's spongy means it's porous. Okay, it contains a lot of pores, the metallic lead, so it's called spongy. At cathode, lead dioxide plus 2 electron gives lead plus sulfate gives lead sulfate plus 2H2O, which is plus 0.1685. So the EMF produced by the cell is 2 volts. Okay. Okay. So we have seen this. So this is the overall reaction. Lead dioxide plus lead plus 2H plus 2HSO4 minus gives 2 lead sulfate plus 2H2O. If one cell develops 2 electron, so normally it has a 6 or 12 cell battery connected in series, which will develop 6 into 2, 12 volts. See, for example, these are all in series like this. See, if you have, this is electrolyte, H2SO4 to fill the battery case. And these are all like this and this and this. This combines to give, you have cathode, positive lead grids filled with lead oxide. Whereas these ones which are here, okay, these are all anode, negative lead grids filled with spongy lead. So this is how it is stacked in series, one after the other, and the whole thing fills the battery case with H2SO4. Okay, this is just a schematic representative diagram how the electrodes are stacked. Okay, we have seen in the previous picture that the overall with the case, with the outer case also, and here this is the inner picture. Okay, so lead acid battery, as we all know, it is used in many places, commonly in car batteries, in inverter batteries, UPS batteries, etc. What are the advantages of this? It is available in different shapes and size. Obviously, its advantage, and this majorly doesn't require any maintenance is another advantage. It is best in terms of reliability, working capabilities. Okay, so that we know already. We have emphasized lead acid battery is still used, even though lead is environmentally hazard. Their widespread use is still there because of its performance and low cost, which is very difficult to replace by any other system. Okay. So it withstands slow, fast, and overcharging. Okay, it is more rigid to withstand slow, fast, and overcharging. It is capable to withstand long-term inactivity with or without solvent. That means you can keep the battery in the charged condition without using for a long time, for a quite long time. In some batteries, what happens? There will be something called self-discharge. Without using the battery itself, the battery will lose some of its charge, okay, or some of its active material in the form of it is discharged, automatically discharged. It's called self-discharge. So that self-discharge, okay, it's less in lead acid battery. It is capable to withstand long-term inactivity with or without solvent. It offers best value for power and energy. We have emphasized already, kilowatt hour. And another thing is, about 97% of lead can be recycled and reused in new batteries. Okay, these are all we have already told, inexpensive, simple to manufacture. It offers low self-discharge. That's why we can it can be capable to withstand long-term inactivity with or without solvent, which is lowest among rechargeable batteries. That means compared to other rechargeable batteries like nickel metal hydride, nickel cadmium, where the self-discharges are more comparative to lead acid. It offers good performance at low and high temperature. Okay, it offers better performance compared to other batteries at low and high temperature. Okay, what are the disadvantages? Lead is heavier compared to other elements. As I told, we can also say lead is heavier metal. It's a heavy metal, means called it's a poisonous to environment. So lead normally people avoid, okay, but here because of its characteristics and high usefulness and inexpensiveness, it is still people are using this lead acid batteries. Okay? It can be charged slowly, that is fully saturated charge takes 14 to 16 hours. This is one of the disadvantage. Okay? This is one of the disadvantage. It takes 14 to 16 hours for fully saturated charge. That is means a battery to need to fully charge, it takes quite long time compared to other batteries, 14 to 16 hours. It must be stored in charged condition to prevent sulfation. Okay, sulfation because we have seen both anode and cathode reaction leads to lead sulfate. Okay, so the sulfation has to be avoided. In order to prevent this sulfation, charged condition is, it must be stored in charged condition in order to prevent sulfation. Okay, and limited cycle life is one of the disadvantage. Charged condition, you have to keep it to prevent sulfation is a disadvantage. Limited cycle life and repeated deep cycling reduces battery life. It's also it's a major disadvantage in terms of cycle life. And flooded version of battery, we call it as a vented type, requires watering. You have to like periodically after some use you have to water. Okay, you have to add distilled water into the through the there will be a place where you can add distilled water to increase the electrolyte level. Okay, environmental friendly, we have already told, it's a heavy metal, poisonous to environment. And transportation restrictions are there in flooded type. Okay, because it's a fluid type, liquid type battery, flooded type battery. So there is some restriction for transportation, safe transportation due to safety. Okay. So next we come to the, so far what we have seen is lead acid battery. So with that we will move to the lithium-ion battery, which is very important battery system, secondary battery system, lithium-ion batteries. And we are always hearing nowadays lithium batteries are used everywhere. Without lithium-ion batteries, you cannot imagine any modern electronic gadgets, whether it be a laptop or whether it be a cell phone or whether it be Android cell phone or anything. Lithium-ion battery plays a major role in all latest recent technologies. Okay, so now we will see as a secondary batteries, lithium-ion batteries, how it is, what is its working and construction like that. Okay, okay. Why lithium? Why lithium is so good in bringing? Normally, we know that it gives higher voltages. Why? Because lithium is small in size, it's third only to hydrogen and helium, so it's lightweight. Lithium-ion batteries are capable of having very high voltage. It can give 4 volts. Okay, comparatively higher to many other, compare all other batteries. And charge storage per unit mass and volume is high. So lithium-ion batteries are capable of having a very high voltage, and charge storage per unit mass and unit volume is also high. And lithium-ion can use a number of different materials as electrodes, which we will see. What are the cathode materials? What are the anode materials we can use in lithium-ion batteries? Okay. Okay. So as I told, from laptops to cell phones to hybrid cars to electric cars, electric vehicles, lithium-ion batteries is very popular due to its lightweight, high energy density and ability to recharge. Okay, so these are all the plus points for lithium to be used in lithium-ion batteries. There are a lot of research going on for any other better characteristics or any alternative to lithium-ion batteries also going on. But as of now, in the market, lithium-ion battery is the best available technology. Maybe down the line in future, you may get some other alternative, but still lithium-ion battery has its own advantage and very good uses at present. Okay? So this is very popular due to lightweight, high energy density and ability to recharge. Okay, cathode in lithium-ion secondary batteries, cathode is intercalated lithium compound, such as layered lithium cobalt oxide, like that. Okay, intercalation chemistry. Okay, what is meant by intercalation? Or layered lithium cobalt or layered metal oxides. Okay, see, for example, you have metal layered structure, like there is a layer here, okay, in the structure, and then another layer like this. So there are some gaps in between these two layers where a lithium can go and sit, where a lithium and go and get stored. Okay, so that's why where we can able to uh, make the lithium come and sit at the same time, make the lithium go out to the other side of the electrode. So this acts as actually like a host guest, that lithium acts as a guest for the host layered structure. So the in between the layers, the lithium can come and insert itself and it can go out itself. That is that type of chemistry. It's called intercalation chemistry. It's called intercalation chemistry. So where lithium can intercalate into the layered metal oxides, and then where it can be like it can act as a stored place. Once if everything is discharged, then lithium move towards the other electrode. We will discuss all those things. So as we told already, 4 volts EMF it can give. Anode is lithium doped graphite. Mostly cathode you have variety of materials, a layered lithium cobalt oxide, and we have other metal, other transition metal oxide layered structure are also used nowadays, or also used as cathode. Typically, lithium cobalt oxide is used in for all commercial purpose and in many places. Anode is typically lithium doped graphite, but there are other systems also available to be used as an anode in lithium-ion batteries. Liquid electrolyte consists of complex lithium compound, lithium PF6, lithium tetrafluoro, lithium hexafluorophosphate, okay, dissolved in an organic solvent such as dimethyl carbonate. All these things should be in non-aqueous. Okay, non-aqueous means water and moisture conditions should not be there. As we all know, it's lithium can catch fire, or lithium can immediately react in the presence of aqueous conditions. So non-aqueous, it's a very important condition, which is normally given by lithium hexafluorophosphate dissolved in organic solvent. This is the most common combination used as electrolyte in lithium-ion batteries, but there are some other combinations of complex lithium compound are also used as liquid electrolyte. So as we told, cathode is most commonly lithiated metal oxide. Okay, we will say lithium metal oxide, where M is a metal, transition metal or any other metal, lithium metal oxide. So there are 3 main types in this: layered oxide like lithium X cobalt oxide, which is hexagonal close packing structure. HCP means hexagonal close packing structure, either cubic close packing or hexagonal close packing. This is hexagonal close packing. And polyanion materials like lithium iron phosphate, lithium 2 FeS, lithium iron sulfate. This is silicate, sorry, not sulfate, silicate, SiO4. This is called olivine structure. This is from the mineral, similar to mineral. Lithium iron phosphate, olivine. Iron phosphate, olivine. So lithium iron phosphate and lithium 2 FeSiO4. And spinel oxides like lithium Mn2O4. These are also, this is spinel oxides. Okay, so we know that spinels Ab2O4 are general structure, general formula. They have manganese in different oxidation states and manganese in different coordination states, like octahedral and tetrahedral, both things. It's a complex crystal structure, spinel oxide. So LiMn2O4, it's a Ab2O4 structure. Okay, So all these things can act as a cathode. In this, lithium cobalt oxide plays a major role. Means this is available in many places as cathode materials. In most of the in today's lithium-ion battery, lithium cobalt oxide is more preferred and it is used. Okay. Anode. One of the most common anode material today is lithiated graphite. Okay. Lithium C6. Okay. Lithiated graphite, which is composed of graphene sheets intercalated with lithium. So we know that there are graphite. It's a hexagonal sheet. They are in the form of sheet like this. Okay, they have hexagonal sheets like this, where the lithium can be stored in between the sheets. Okay, where it can be stored, it can go out or it can come in. Okay. We will see in the next slide what I mean by this statement. Go in and go. Lithium ion can be stored and lithium ion can be moved out of the places in between the layers. Again, lithium graphite is a unit cell with HCP, hexagonal closed packed structure. So anode is lithiated carbon or lithium graphite. Cathode is lithium cobalt oxide. Okay. So there are many different kinds of electrolyte. As we've seen, lithium PF6 in ethylene or methyl carbonate solvent. We have seen dimethyl carbonate. Ethylene dimethyl carbonate is also used commonly. Okay, or you can use ethylene carbonate solvent also. It's a most commonly used solvent. Where there are some other fluorinated complex solvents can also be used, but this is the lithium PF6 in dimethyl carbonate or ethyl carbonate is a most prevalent, commonly used electrolyte today in lithium ion. Okay, now secondary batteries. What is the reaction happening during discharging, and what is the reactions during charging? And we will see this equation after seeing this. Okay, so what is discharge? Discharge, as we have already discussed, is nothing but when the battery is used. Okay, when the battery is used, we call that as in the discharge mode. That is, the battery is in discharge mode or we are in using it. Okay, the power is draining. Okay, so during discharging, lithium is oxidized to lithium plus 0 to +1 oxidation state. In the lithium graphite anode, through the following reaction, C6Li means Li C6 gives 6 carbon in the form of graphite plus lithium plus electron. This is anode. Here what happens? The lithium ions migrates through the electrolyte medium to the cathode. So anodic oxidation, the electron through the normally we have seen in electrochemical cell electron, but here in lithium ion cell, lithium ions migrate. Lithium ions migrate through the electrolyte medium to the cathode, where they are incorporated into the layered lithium cobalt oxide. I have told intercalation chemistry. Lithium will go and sit between the layers of lithium cobalt oxide. So through the following reaction, which reduces cobalt. So this is cathode. Okay. So cathode means, according to this equation, cathode means reduction. So cobalt +4 reduces to +3 oxidation state. So this is the reaction. So during discharging, these two are the reaction. So always we know during charging, this is reversed. Okay. So during charging, these reactions in anode and cathode are reversed. That means this side. During charging, reversed. Discharging, front. Charging, back. Here. Okay. So these reactions can be run in reverse to recharge the cell. In this case, the lithium ion leaves the lithium cobalt oxide cathode and migrate back to the anode, where they reduces back to lithium, neutral lithium, and incorporated into graphite network. See, first what happens? This is anode here, cathode reaction in discharging. Whereas in charging, you will get the reverse. the reactions will happen in the reverse way. So that's what we have shown here. Actually, that's what we have shown here, charging and discharging. So we have seen lithium C6 plus lithium 1 minus X cobalt oxide during discharge gives C6 plus lithium cobalt oxide. Okay, so this is what we have seen during discharge, where this lithium C6 to C6 they have seen as plus lithium plus electron, that is we seen as anode, whereas in cathode lithium cobalt oxide to lithium 1 minus X cobalt oxide to lithium cobalt oxide, where lithium is transporting between the anode and cathode through the electrolyte we have seen. So now the reverse reaction, we call it as charging. Okay, so this is the reverse reaction which is shown here. Okay, so charging and discharging, this is the way. So where lithium ion anode gives first during discharge, anode gives the electron plus lithium Li plus lithium ion, Li oxidized to Li plus. The lithium ion is moving from anode to cathode through a electrolyte, and at cathode this reaction happens during discharging. Okay, so what happens? Lithium cobalt oxide, lithium 1 minus X cobalt oxide plus lithium ion plus electron gives lithium cobalt oxide solid. So they go back to the initial active material, which is lithium cobalt oxide. Okay, so this is during discharging. So during charging, the reactions are all reversed. First, what happens? In this case, in charging, lithium leaves the lithium cobalt, okay, and goes to form lithium 1 minus X cobalt oxide. Okay, this is in cathode. And anode, they are reduced back to form lithium C6. Okay, so this is how this charging and discharging is explained in this lithium ion. So first we have told what is the condition of reactions in anode and cathode during discharging. The reverse is explained in charging. The both in the form of equation we have written here. Okay, so here we see the diagrammatic representation. We have explained that the lithium ion means Li plus ion moves from anode to cathode during discharge, cathode to anode during charging. Okay, so this is anode, this is cathode, lithium metal oxide cathode, lithium cobalt oxide cathode. This is anode, lithiated carbon LiC6. Okay. So this is cathode, this is anode. This is a non-aqueous electrolyte. So we have seen that LiPF6 in dimethyl carbonate solvent, DMC, dimethyl carbonate solvent. Okay. So now what happens during discharging? Lithium LiC6 gives 6C plus Li plus electron. So this electron move from anode to cathode during discharge. This is what we have seen in the previous slide, which is diagrammatically shown here. During discharging, the electron plus lithium plus 6 carbon. This lithium plus ions move from anode towards cathode through the electrolyte during discharge reactions. Whereas during charging, the reverse is happening. Lithium cobalt oxide gives lithium 1 minus X cobalt oxide plus lithium plus electron. So this lithium moves from cathode to anode during charging. Okay, this is what we have seen in the form of reactions in the previous slide. Now we are seeing in the form of diagrammatic. So when lithium, during discharge, lithium moves from anode to cathode. Okay. So electron move towards this side. During discharge, lithium plus ion and electron move towards this side. During charging, from cathode to anode, this side. Okay. So what we have written in the form of equations, we are seeing it in the form of diagrammatic. Okay, uses. Normally, there is no need to much emphasize on its uses. We already know that it has a lot of important uses in electronic gadgets, in all modern equipments. So this uses it's very well known. There is no need to emphasize and explain further. Okay, advantages. Obviously, advantages is more compared to other batteries, but still. Very well known advantages are it's eco-friendly, lightweight, compact, high energy density due to lightweight and efficient electron transport, and maintenance is low. It's more charge cycle life is more, and discharge rate is low. Okay, so these are all the advantages of lithium-ion batteries. Disadvantages, few disadvantages are also there. It's expensive, and protection required over overcharging and discharging. You should not charge the battery beyond the required limit. Overcharging and discharging leads to sometimes explosion, but nowadays it's very safe to use. It's highly safe, but still it's a disadvantage in the beginning stages. It's better to take this production. And it has transportation problems as a disadvantage. Safety concerns. So as I said already, whether it is overcharged or overheated, lithium-ion battery may explode. But it's very, very, very rare. 1 in 1,000 or 1. Nowadays we are not all hearing any cases of lithium-ion batteries explosion because we are using it everywhere. But still, it's a disadvantage. Even if it occurs 1 in 1 lakh, it's a disadvantage. Okay. Sensitivity to high temperature. It's lithium-ion batteries are sensitive to beyond certain temperatures, like you can say 100, 150. Beyond that stage, we call it as high temperature, which is not good for the usage. It's a disadvantage. Okay. So the lithium-ion batteries, for the development of lithium-ion batteries, 2019 Chemistry Nobel Prize was given to these three scientists, J.B. Goodenough, Stanley Whittingham, and Akira Yoshino. These three scientists have worked in lithium-ion batteries for quite a number of years, for last 5 decades or so. So they got Nobel Prize in 2019 for the development of lithium-ion batteries. This is for information. Or if you already know, it's okay. Otherwise, you can get to know. Okay. So with this, the secondary batteries discussion is over. We will see in the next session corrosion. Okay, corrosion, or corrosion is the next important engineering part in the electrochemistry. So we will start with corrosion in the next class. With this, the session is over.
Like, share and subscribe. Hit the bell icon for more updates.